Hi everyone, I'm Bhattacharjee. I have been working as a visiting researcher at SNBOS National Center for Basic Sciences. The work I'm going to present here has been conducted there primarily. Now, the primary focus of this particular work has been in trying to figure out what can be the origin of QPOs or quasi-periodic oscillations in accreting neutron stars. Now, we go about this problem uh, by taking different approach. We look into the observational data, check what are the basic properties of QPOs in neutron stars. We compare them with the cases of other compact objects, especially black holes. We look into the theoretical literature that is available, what approaches people have taken, what are the pros and cons of different approaches, and try to combine or come up with a solution which is based on theoretically sound approach and which can explain the observational aspects found in nature. In order to do so, we first ask ourselves, what do we know about the QPOs in neutron stars? Now, there are clearly two types of QPOs. You can see in the left panel, there are a number of peaks in the power density spectrum of a neutron star, accreting neutron stars time series or light curve. Now, the low frequency part, here the LB, LLF, and LLF2, these frequencies have a 1:1 correspondence with the cases of black holes, which is seen in the right two panels. You have A, B, C type QPOs in black holes, and you have the flaring normal and horizontal branch oscillations, and they have a 1:1 correspondence between them. However, for neutron stars, you can see there are three other modes denoted by the high frequency QPOs, which are dominantly present in the higher frequency range. They are stronger in the cases of neutron stars compared to black holes if they are present in the case of black holes. So we clearly see there are certain similarities, there are certain differences. So it's quite natural to ask, can we get a solution which is applicable for both the cases? And can it be a generalized kind of solution? Now, people have been looking into this sort of thing, and one of the approaches that people can take is that the frequencies are generated in the accreting flow itself. It's not coming from the star surface, otherwise it would not be present in black holes. It is not due to the anchored magnetic field in neutron stars, because it is also not present in black holes. And also any clumpy structure which can be spread out or smeared out in a few dynamical time scale cannot be a steady state configuration as well, which is needed to generate the sharp peak natures of separate ABC type QPOs. Now, in order to do so, the theoretical approach that we take is that, how do we go about it? Should we start from a minimalist point of view, add components which are necessary, or go for the most generalized case? Now, the most generalized case would be take the generalistic approach for the geometry, take a magneto-hydrodynamic setup for the fluid dynamics, and include Monte Carlo simulation for the non-local processes. Now, this is computationally extensive and maybe even impossible to converge in a real time scale. So what we did was take the minimalist approach. We considered only hydrodynamics, added cooling and viscosity wherever needed, considered a pseudo-Newtonian geometry which can mimic the effects of general relativity to a good approximation, and only included the Monte Carlo simulation when it was necessary. So we did that for the spectral simulations, but for the timing case, we only focused with hydrodynamics with cooling and viscosity. And we tried to see, can there be a generalized solution for that? Can we also explain, let's say, by starting with the QPOs? So to do so, the hydrodynamic setup was quite simple. It was a smooth particle hydrodynamics setup where particles or pseudo particles, which looks like torus in an axisymmetric system, are injected in the RZ plane, and at the center of the plane is sitting the neutron star. Now, in this sort of a setup, we solve for each blob of particle or each torus Navier-Stokes equations, that is the conservation of mass, momentum, and energy. Now here we introduce a term for the surface of the neutron star through the temperature, which is derived from the accretion itself. So dynamically, the amount of energy dumped at the star surface is converted to a black body emitting radiation, which is in turn affecting the effective gravitational pull. So what we get, we see that the temperature of the star's surface, seen in the left panel, is fluctuating with time when you include that effect. And you can see clear oscillation in the time series or light curve that you can think of this as a light curve. We'll go to the exact light curve later on. And if you look at the right panel, you can see both outer and inner shocks are forming. So multiple shocks in the simulations are shown. You can see outflows forming just inside the outer shock region. You can see flow is merging. There are multiple instabilities close to the inner shock region. Now this is a typical case. This is done for a specific angular momentum of 1.8. What we do afterwards was see the density profile, first panel, temperature profile, second panel, both show that near the star surface, the values are very high. They go by order of magnitude. Now, if you look at the last two panels, you can see there's a marked with the arrow, there's a vertical oscillation going on. Now, this lambda 1.8 is crucial. It was also shown for black holes in multiple previous works that it is sort of like the angular momentum where the instability start to kick in. So we see the vertical oscillation taking place here. So it can be clear that if you look at any quadrant on the top layer or the bottom, you can see that matter would be ejected in up and down, upper and lower quadrants. And if we can take the amount of matter ejected, club them, we can actually get some sort of a time series. And if you also take the cooling, so we introduce Bremsstrahlung cooling here. If we just club all the energy emitted at all regions, sum them up, which is more or less a realistic case because you don't have the luxury to select regions from where the energy you are going to count. You can differentiate in terms of frequency, you can differentiate in terms of when they're arriving, that's a different issue, but you cannot spatially separate out energies based on which region it is coming from in observation. So what we do is we take the average or the total emitted energy for the system. So in the left panel you see the mass outflow, in the right panel you see the energy emitted, and we take the power density spectra and we see there is a 1:1 correspondence between the frequencies seen here, and you can also see the harmonics being present. So this shows clearly that the vertical oscillation can generate the hectohertz frequency, which is between 100 and 200 hertz. This is very crucial because in many of the systems, especially wind dominated systems such as Sussenes X1, these frequency in that particular range is very dominant. And this is coming from a purely subkeplerian flow with high angular momentum, but less than Keplerian. Now what happens next? If we change the angular momentum from 1.8 to 1.7, we see the outer shock moves inwards. The stronger inner shock also generates outflows from the post-shock region. And if you look at light curves shown in red and black, that the frequency of oscillation increases. So the radial motion is actually creating high frequency QPOs here. Now if we let the parameters vary, such as the angular momentum, the accretion rates, the radius of the star is varied slightly between 3 and 4, and slightly increase the amount of cooling present in the system by varying the Bremsstrahlung coefficient t to the power half to some other parameter alpha, we can see that we can actually capture all 5 modes of 2 low frequency, 2 high frequency and 1 hectohertz QPOs. And the numbers that we are getting are in the exact ballpark as that found in the real observations. So we can actually get, okay, we can produce some of the QPOs. Now the question is, can we also generate the spectra, or can we generate the seed photons from which this is coming? Is it a stable configuration? Is it the most generic configuration? Because we only tried with the inviscid case. We can see the region which is responsible for generating QPOs is present, but can we also generate the seed photons? What happens if there is viscosity in the system? Now this is a generic question, and many of the people have previously tried to answer this. So what we theoretically check first is that if we introduce viscosity in the system, because there is viscosity in real system and the density near the star surface is very high, so it's quite natural that viscous effects would kick in. We see that with the increase of viscosity from left to right, the flow becomes more stable on the equatorial plane and the density piles up to a higher degree near the star surface, which is seen in the last panel as well. Now what happens as a consequence of that, matter resides in the equatorial plane or near enough to have the its angular momentum readjusted. So even if you start with the subcapillary flow, it would readjust itself so that it would match the inner boundary condition, and the angular velocity would have to match with the star's angular velocity. Now here we stumbled across another interesting thing which can also address some of the timing properties as well. Now the n-ball or normal boundary layer in our terms, is it the unifying layer that we are talking about? Now why am I calling it the unifying layer? Because there are three approaches that people have taken in explaining the angular momentum readjustment on the star surface. One approach is matter with whatever angular momentum coming in, it reaches the star surface and changes the star spin as well. This is typically found in observation that the spin up rate can be a spin up or spin down rate of different neutron stars can be determined, which means not just the flow, the star itself would undergo an angular momentum readjustment. So for that cases, delta omega ns is not equal to 0. The second is the star, maybe it's too heavy, considered to be too heavy, or the angular momentum that is imparted is not great enough to change the scenario, which means the matter has to adjust with the star's angular motion, which means there is a, and one of the proposition is it happens on the star's surface through a 2D spreaded layer on the boundary. It's very thin layer, there's no vertical extent, so it spreads on the surface. The third one is transition layer, which demands that if you have enough viscosity, matter would try to readjust its angular momentum well before it reaches the star's surface, and you will have a radially spread transition layer. Now, these are the three scenarios that are possible. But what we find is that if you start with an inviscid flow and just vary the viscosity parameter, you can actually arrive at all three of those cases. Now, the number one case has already been studied by us in a previous paper where we just studied inviscid case. Even for the case and we determined the spin up rate and we found that to be in the same ballpark figure that is found in observation. The second two cases can be seen in the left panels. Now, when the viscosity is low enough, let's say case C1, you see the blue region very close to the surface is actually coming from the subcapillary and a very thin layer where the angular momentum is readjusted. This is equivalent to the spreading boundary layer. But if the viscosity is relatively higher compared to that and maybe near to a critical point, you can see in the red curve or the black curve, Keplerian disc-like structure is forming first, and then you have a Keplerian to subkeplerian transition. This has already been reported as a transition layer by Titachuk and the co-authors in 1998. The spreading layer was reported in 1999. So what we are finding here is a generalized transition behavior intermediated by viscosity, which can either produce the boundary layer or the transition layer based on the amount of viscosity in the system. N-ball encompasses all these three cases and connects them with a varying viscosity. Now, if the viscosity also has a z gradient, then the region with higher viscosity, if it is beyond a critical value, as we have taken in our case, it can form a disc-like structure along the equatorial plane. We see in the left and right panel that along the z is equal to 0, the equatorial plane, Mach number is low, a Keplerian-like disk is forming out of the subkeplerian flow, which is undergoing a shock in the outer region of, let's say, 22 to 23 Rg, and an inner shock near about 4-5 Rg. So the subkeplerian flow is also present, the Keplerian flow is also forming, which means this is forming the two-component effective flow, which is also seen for the cases of black holes. This is the first time we're reporting such a thing. Now, the subkeplerian flow does have the property of generating QPOs. If you have further included cooling, strong cooling, you can actually see the disc-like structure being formed. If you turn it off, you can actually see it reverting back to the subkeplerian flow. So the takeaway from it would be that if you have a purely hydrodynamic simulation setup, which includes cooling and viscosity, you can actually have a generalized structure like two-component effective flow form in the setup, and which can explain the origin of different modes of quasi-periodic oscillations or the peaks in the power density spectrum for neutron stars. Thank you so much.